For most of human history, information could only move as fast as a person could carry it on a horse or a ship. Today, trillions of bits of data cross the globe instantly through invisible networks. This control over information began with a simple observation in ancient Greece. Thinkers like Thales of Miletus noticed that rubbing fossilized tree resin, or amber, allowed it to pick up light objects like feathers. They called it electron, the root of our word for electricity. In 1831, Michael Faraday turned that static spark into a tool by discovering electromagnetic induction. Induction is a process where a changing magnetic field creates an electrical current in a nearby wire, finally giving us a way to generate a continuous flow of power. That power led to the telegraph, which used electrical pulses to send messages at nearly the speed of light. But as this crowded operator room shows, the system was limited by its reliance on manual clicks. It could transmit short bursts of text, but it lacked the sensitivity to carry the human voice or complex data. Generating raw electrical power was only a starting point. To move into a truly connected age, we had to find a way to detect, manipulate, and boost those incredibly weak electronic signals. As the 1900s began, engineers faced a massive hurdle: finding a way to send the human voice wirelessly through the air without the signal fading into static. In 1906, Lee DeForest developed the Audion, a 3-element vacuum tube. It worked like an electronic valve. By using a tiny signal to control a much larger flow of electrons, it could amplify weak radio waves millions of times. This ability to boost signals made radio broadcasts and long-distance phone lines possible. It even provided the switching logic required for the earliest electronic computers. However, these tubes created a massive physical bottleneck. They were made of fragile glass, generated intense heat, and burned out frequently. A single machine required thousands of tubes, filling entire rooms just to perform basic calculations. While the vacuum tube gave us the power to amplify signals, its physical bulk and heat output set a ceiling on how complex our technology could become. In 1947, a team at Bell Labs found a way to move past the glass tube. William Shockley, John Bardeen, and Walter Brattain successfully demonstrated the first solid-state transistor. The transistor performed the same job as the vacuum tube, but it was tiny, durable, and ran cool. It allowed engineers to build much smaller devices, leading to the first portable radios that could fit in a pocket. But shrinking the parts created a new problem known as the tyranny of numbers. As machines became more complex, thousands of individual transistors had to be wired and soldered by hand. The more components you added, the higher the chance that a single bad connection would cause the entire system to fail. We had solved the heat and size problem, but we hit a manufacturing wall. We could not build a digital future if every single connection had to be made manually with a soldering iron. By the late 1950s, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor arrived at a solution to this wiring crisis. They developed the integrated circuit. Instead of wiring separate parts together, they realized they could carve all the components, the transistors, resistors, and capacitors, directly into a single block of semiconductor material. This shift meant that the connections were etched into the silicon itself, completely removing the need for physical wiring between parts. This made the mass production of incredibly complex circuits possible for the first time. The integrated circuit broke the link between a machine's processing power and its physical size, clearing the way for technology to shrink even as it became more capable. In 1971, this evolution reached a turning point with the release of the Intel 4004. This Intel document identifies the 4004 as the pioneer microprocessor, a programmable logic microchip. Before this, chips were hardwired for one specific task. The 4004 was a general-purpose processor that could be adapted to almost any function. This was the moment hardware became software. Instead of building a new physical circuit for every new task, engineers could use one chip and simply change the software instructions it followed. The microchip didn't just make things smaller, it created the architecture of modern computing, where logical instructions replaced physical wiring. Today, the impact of these microscopic chips is visible on a global scale. They drive everything from the smartphones in our pockets to the complex systems required for space exploration. This is the result of an unbroken chain of human ingenuity. We have moved from Thales of Miletus rubbing a piece of amber to a world powered by billions of programmable processors. By mastering the movement of the electron at the atomic level, we have shifted from a world of physical limitations to one where our only real boundary is the logic we can imagine. To start your career in electronics, visit Mr. Circuit Technology.